Assalamualaikum warahmatullahi wabarakatuh. A very good morning to Ibu Asrianti PhD, Head of Center for Educational Assessment Agency for Standards, Curriculum and Educational Assessment of the Ministry of Education, Culture, Research and Technology. Professor David Andrich from the University of Western Australia, Bapak Bahrul Hayat PhD, Vice Rector for Academic, Student Affairs and Human Resources at Indonesian International Islamic University. Bapak Bambang Sumintono PhD, Head of the Doctoral Study Program in Education at the Faculty of Education at Indonesian International Islamic University. Distinguished guests, ladies and gentlemen. Welcome to the public lecture with the theme of The Paradigm of Rasch Measurement Model and its Application. This event is organized by Center for Educational Assessment in collaboration with Indonesian Educational Evaluation Association and also Indonesian International Islamic University. My name is Anissa, and on behalf of the organizing committee, I would like to extend our highest appreciation for your participation. Let us now turn our attention to the national anthem of Indonesia, Indonesia Raya. Ladies and gentlemen, please join me in welcoming Ibu Asrianti PhD, Head of Center for Educational Assessment Agency for Standards, Curriculum and Educational Assessment. Dr. Yanti will deliver the opening remarks. Dr. Yanti, the time is yours.
Thank you. Ladies and gentlemen, distinguished guests, partner, and fellow learners, good morning. Today we embark on an intellectual journey that hold the promise of deepening our understanding of measurement. We are honored to gather here for an online public lecture featuring one of the most eminent figures in this field, Professor David Andrich. The spotlight of today's discourse is the Rasch model. The power of this model is profound, touching the very essence of how we conceptualize measurement, how we quantify human attributes and abilities, and its application ranges from education, social science to healthcare. The model is a measurement model rather than statistical model. This distinction between these lead to the notion of the RAS paradigm, as will be elaborated by Professor Andrich. Professor Andrich's lifelong dedication to this model and its wide range application has not only expanded our horizon, but also set a benchmark for rigorous measurement practices. He has conducted extensive research in this area and has made substantial contribution to the development and understanding of this model. We extend our sincere appreciation to Professor Andrich for sharing his wealth of knowledge with us. In fact, I'm personally grateful that in his tight schedule, he's willing to spare time for this lecture. Thank you, David. The original idea for this lecture is for postpendic staff as an introduction of the RAS model. But then it is considered that many researcher students might be interested in hearing the RAS model from the expert who not only had the opportunity working with Georg Rasch, but also consistently working on the RAS model with result in numerous publications, ranging from philosophy of measurement, development through model and exposition, and interpretation to software development. In fact, just recently, Professor Andrich published a new book. The registered participant for this lecture reached to around 600, increased by 20 times from the original plan, and coming not only from Indonesia, but also from overseas. This is as a result of collaboration between Center for Educational Assessment, Pusmendik, Indonesian Educational Evaluation of Association, HEPI, and Indonesian International Islamic University, UIII. We thank you, Pak Bahrul Hayat, Pak Bambang Sumintono, Pak Eviana, and all Pusmendik teams for all the support in making this event possible. We thanks all for being a part of this enlightening experience. We hope that this lecture will give some insight to increase the quality of measurement. Thank you.
Thank you, Dr. Yanti. We will now continue with the welcoming remarks by Bahrul Hayat, PhD, the Vice Rector for Academic, Student Affairs, and Human Resources at Indonesian International Islamic University.
Thank you, Anissa. Our distinguished speaker, Professor David Andrich, Bu Asrianti, and my colleague from the Center of Educational Assessment, the Ministry of Education, Culture, Research, and Technology, my fellow members of the Indonesian Association of Educational Evaluation, HEPI, and my fellow faculty members of the Indonesian International Islamic University, distinguished participants, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to all of you. Welcome everyone to this online public lectures. We are very honored to have you all here. And we are all here because this public lecture brings an important topic. There is something we are passionate about, especially for psychometricians, as well as educational, psychological, and social measurement specialists. The next hours will be full of fascinating ideas and concepts from Professor David Andrich, a prominent person behind the development of the RAS measurement model. Personally, today is indeed a very happy day for me and of course for all of you, because David agreed to give a special lecture this morning. So on behalf of the Indonesian Association of Educational Evaluation and the Indonesian International Islamic University, I would like to extend a warm welcome and express our gratitude to David for being a special speaker at this public lecture in the midst of his busy life, and for his willingness to share his exceptional knowledge and experience regarding the Rasch measurement model. Personally, I first met David more than 30 years ago in 1990, while I was working on my doctoral degree with Ben Wright at the University of Chicago. So Ben has a nice habit of consistently inviting notable former students, including David, to his Rasch measurement seminar and classes. For this public lecture, we are very grateful for the cooperation and support of Bu Asriyanti, the Director of the Center for Educational Assessment, the Ministry of Education, Culture, Research and Technology, in organizing this morning open lecture. We also appreciate everybody who prepared and assisted with the planning of this event. So finally, let's make the most of this rare opportunity, and I appreciate your coming and hope you have a great time with David. I thank you all and may God bless you. Assalamualaikum warahmatullahi wabarakatuh. Back to you, Anissa.
Thank you, Dr. Bahrul, for the welcoming remarks. Ladies and gentlemen, let us proceed to the lecture on the paradigm of Rasch measurement model and its application. It will be delivered by Professor David Andrich from the University of Western Australia. This session will be moderated by Bambang Sumintono, PhD, who is an expert on educational policy and educational management. Dr. Bambang now serves as head of the doctoral study program in education at the Faculty of Education, Indonesian International Islamic University. Dr. Bambang, the time is yours.
Okay, thank you very much, Mbak Anissa. Good morning, everyone. It's really happy to become a moderator for this session. Okay, we have Professor David Andrich from University of Western Australia. I will inform a bit about his background. Okay, so David Andrich is graduated from in mathematics from University of Western Australia. Then continue PhD in Mesa program, University of Chicago in 1973 under Professor Benjamin Wright. Okay. At the same time, he also got a postdoctoral with Georg Rasch. Okay. I think he's one of the legend when we talk about polytomous Rasch model with rating scale model. We are formulated by David Andrich. Prof. Andrich, actually, my background mostly I train as qualitative researcher. Then when I become a lecturer, so I have to study Rasch measurement because one of my students actually asking me to guide her in terms of item analysis. Then I just falling in love with Rasch model and more, and the thing that I study, what you call is very enlightening for me, right? So Dr. and Professor Andrich already published so many books, research papers, report. I think the last book that already mentioned by Bu Asriyanti is about Rasch metameters. Okay, so it's very interesting to read that book also, understanding about another aspect of Rasch model. And also David Andrich developed one software, RUMM, Rasch unidimensional measurement model, will be one of the standard for Rasch measurement analysis software. All right, so without further ado, so I think Dr. Andrich, the screen is yours to start.
Good morning. Can you hear me?
Yes, good. Good. Yes, okay.
Thank you very much. Now, so thanks very much for that introduction. And in fact, you mentioned 1973. So it's 50 years ago that I graduated with my PhD from the University of Chicago. If you say half a century, that sounds a long time. I've enjoyed the journey, and amongst my students, of course, is Yanti. So thanks, Yanti, for organizing this and being such a good student and a executor of Rasch measurement. So again, thanks to everyone and all those introductions. And I hope that you'll get a flavour for the issue of paradigm. And I have two papers on the topic that I'll give to Yant. He's got, maybe has them already, but I'll make sure she has them after the lecture. And you'll be able to read some of these issues in greater detail. So can we, is someone else, is Elisa going to put my PowerPoint up, or do I have to do something?
I think maybe the organizer will share the screen.
Yeah.
Yeah. Teman panitia bisa share PowerPoint?
Yes, wait a minute.
Yes.
Okay, this is like applications. I've changed the title a little bit to be measurement theory as well as the model itself, because over the 50 years that I've been working on this, I have also published on why this is a real theory, not simply a model. So thanks very much, and shall I be the person who now proceeds with the slides? It's now, oh yeah, here we go. So Georg Rasch, is this working with me, or is this, I'm pressing the button to continue, but it's not happening. Here we go. This is what we're going to do. His major insight, a perspective on social measurement. I'll give a very simple application of this to get to the point. We won't be dealing with a lot of statistical theory and modeling and expectations and estimation and so on. It'll be an elementary application, but the basis of all the power that we see in other examples. And I'll give you, oops, that's gone too quickly. It's not really working 100%. I'll give some sources, evidence of controversy, and why it can be controversial, and the differences in paradigms. We have used the word paradigm. It's not really working like it was before. The concept of a paradigm is from Thomas Kuhn, a philosopher of science, and it's about the assumptions that are generally not stated. They are hidden. Everyone takes them for granted. And these assumptions between paradigms can be incompatible. And because they're incompatible, because they are very different, we end up with controversy, because the arguments about which paradigm might be better. But usually the arguments do not appreciate that it is about assumptions. It looks like it's about the detail. So, and I've tried to make explicit why there is controversy, and that it is more than just an argument about the detail. And this lecture will have one component of the lecture will be on this issue. As in the title, Yanti requested that I do this rather than something on technical issues, and of course I enjoy doing these. So the two papers have just come up, and these are the two papers I'll make available. You can download them, I'm sure, but I'll send a PDF to Yanti. One explicitly controversy, and the other one is that this controversy arises from two of the most famous statisticians that were around at the turn of the previous century, and this controversy existed between these two famous statisticians. So it's not just between Rasch and pro-Rasch. This is a very deep topic. It's statistical, but it's also philosophical. So if you want to get into more detail or more interest in the philosophy of this, these two papers are where I have written a fair bit. There is a third one as well, and maybe I can send that one, that is specifically on the ordered category model, the rating scale model. Okay, so Rasch first did his work at the Danish Institute for Educational Research. Now, he was a statistician. He worked in biological and other sciences, but was invited to act as a consultant to the Danish Institute for Educational Research. So it was an educational problem that he was engaged in. And the problem was to monitor the progress of reading of students who had been diagnosed as having problems in reading. And that, of course, is a very modern topic. It's a topic that's always relevant, is the study of change and growth and so on. And it's 50 years after my PhD that we published a book on growth as analysed from the perspective of Georg Rasch. But a journalist, when this was made public in Denmark, and there's an article from a journalist I have, but I thought I would give this quote: "This groundbreaking work will be studied and employed not only in Denmark, but in the whole world." And it's turned out to be true. It's studied everywhere. But there was both a very strong reception and a very strong rejection. The strong rejection mostly comes from US and a little bit of English. Continental Europe had much less problem, and we could get into even that topic about a perspective of science from the continental European, Asian, and that world compared to the Anglo-Saxon world of the US and England. So, but we won't go that far. Basically, it's an empiricist world. That is where you collect a lot of data and you hope you find something, versus you have a strong theory and you go and see if you can confirm the theory. That's the basic difference. Anyhow, so there's a strong reception and a strong rejection, and hopefully I can bring up. And as an example, references of Rasch up to 2020, if there's a reference in the title or the abstract, this is the rate of increase of papers that shows. So in 2020, there were 450 papers that had the word Rasch either in the title or in the abstract. Remarkable. A lot of people don't think that Georg Rasch, in fact, was a real person. They think Rasch is some term. So am I bringing this up, or is the coordinator bringing this up? Because if that's the case, that would be good. Anyhow, so he studied, in fact, with Fisher, and I've already mentioned these two statisticians, Fisher and Pearson. They were in London at the same time. That Pearson a bit older than Fisher, but they also had very strong paradigm arguments. Okay. So what Rasch worked out was, and simply summarized all his work on the growth of children's reading, that for measurement, a comparison between two objects should be independent of the instrument and independent of which other objects are compared. So if you compare the heights of two people, it should not depend on which ruler you're using, and it should not depend on anybody else that you might want to measure, or if you want to measure the weight, or if you want to measure the temperature. And the same with respect to the instrument. So this, and what made other psychometricians or measurement people who worked on measurement in the social sciences were close to this requirement, Gutman, Thurston, and some others. But what was really important for Rasch's work is that he was a mathematician and he could turn this requirement into a mathematical statement. And hence all the work that follows is because we could make derivations based on the mathematical equation. And that's the point of mathematics, is that you can make derivations and you can study the consequences in a very formal way. So this important about the invariants, I'll illustrate with a very simple example, but they are actually real data. I've just taken 3 items from a statewide test in elementary measurement of elementary mathematics. So here we have there were 65 items, but 35 were given to year 3. You can see that these were the common items, and items 36 to 65 were given to year 5. So this is the structure. Now, in fact, there were many, as you see, 30 items. I'm just going to take 3 items, one from this set. Okay, so I'll take item 131, item 140, and item 127. This item here is the common item. Next slide, please. So just quickly, this is what the question looks like for year 3. Next question, next slide. This one is, we don't need to know the details, but you can see they are, this one looks a bit harder. And next slide. And that looks a lot harder. So basically, can you put item 140, which is very hard, on the same scale as that easy items that we gave to year 3? So this is what permits the study of growth. This is what permits putting people on the same scale and putting the items on the same scale. Thank you. So just conceptually, you take one student, a theoretical student, and you want to have a look at the possible responses for the common item 131 and the easy item 127. And the possible responses are simply both wrong. The first wrong and the second right, the first right and the second wrong, or both right. Now, from this response pattern and this one, you can't tell which the student found more difficult. As far as the data are concerned, the student found both items so difficult that the student got them wrong. And these were so easy that they got them right. But these pair of responses, if the student responds like this, and item 131 for that student was easier than item 127, and the other way around. Here, item 131 is item 127 is correct and item 131 is wrong. Okay, so this is the elementary. You can get into very fancy statistics from this, but this is the core. And it's been mentioned that I did study with Rasch. I heard him give a lot of lectures, and all his lectures started here. Okay, thank you. So it's just those two patterns that are relevant to us. Now, this is a bit of a start of some of the controversy, because here we're saying we're going to not use some data. From some perspective, but these are data, you should use them. But we say, from the point of view of getting the relative difficulties of the items, those data are irrelevant. And from some paradigm, the idea that you've collected data, but it's irrelevant, starts immediately to raise concerns. Okay. So from these data that we had, we actually found 1131 students, sorry, item 131 right and the other one wrong, 393. And item 127 more difficult, 58. So one's a lot more difficult than the other in general, and the ratio is either 0.15 or 6.45. So item 131 is quite a lot more difficult than item 127. Of the people who found got one of those two wrong, 58 got this one right and this one wrong. So this one is much harder than this one. 131 much harder than this one. Okay. And notice you can make that a ratio. And I won't go into the details, but the difficulty of item 127 over 131, if you parameterize, give a parameter to the difficulty for this item relative to the difficulty of this item, it's like this. And you can say all these things. The relationship between the difficulties of the items. But it's just a relative difficulty, not an absolute difficulty. Thank you. Now, what I've plotted here is from the whole lot of data that we had, the total number of more people got the items right from the whole population, different levels of achievement. What's the ratio of the difficulty of these pair of items? And you can see it's along very close to this straight line. This line is the ratio 58 to 383. And along here is when you cut the data up into class intervals with people who've got it many right and many wrong. So you see that ratio is relatively consistent. There's a little bit of a bigger ratio here for the more difficult item. Okay, so the point of this title was that the relative difficulty is invariant along achievement. What about if we break it up between boys and girls? Is the ratio invariant for boys and girls? Well, the boys and girls are this ratio, boys this ratio, and the girls this ratio, and the total is this ratio. You don't need to do a chi-square statistical test to say the ratio is invariant. The relative difficulty of the two items is the same for boys and for girls. That's an important test that the item is working as we require. Because if that's not true, then the girls and boys are finding them differently difficult. So it's going to be hard to say the girls are better at mathematics than boys or the other way around because they're finding them different. Okay. So we can conclude that in the group of boys and girls, the relative difficulty is invariant. It's the same. So it's the same across different proficiencies and the same for boys and girls. So that's two very important pieces of evidence that this item is working as required. We can go a bit further. Now, this is where, and we'll get back to this, what if it didn't work? And this is where there's a big paradigm difference. In anticipation, if this doesn't work, in the Rasch paradigm, the Fisher paradigm, you would look at what is the wording of the item, how was it presented, did the girls find something in it that the boys didn't, and so on. If you were in the statistical paradigm, you somehow just simply try to model the difference. You don't get yourself concerned with the quality of the item and so on. What you do is you think of it as a statistical problem, not as a test design problem. So we'll come back to that a little bit later again, but it's the theme of the talk, so I'll highlight it as we go. So now we've got back to these three items. We'll try and do the same thing for item 131 and 140, this item and this item. And in fact, if you take those two items and you take different proficiencies, I've just summarized it differently, low proficiency overall of all the students, middle proficiency and high proficiency, this is the ratio. Again, you do not need a chi-square test to tell you this ratio is effectively the same for different proficiency levels. And what about boys and girls in year 5? Very consistent ratio as well. So now we can proceed to use the power of the Rasch model, because across different proficiencies and an important background variable are boys and girls. We could do it other ways as well. In Australia, for the so-called NAPLAN tests, they break it up by state, they break it up by Indigenous, by kinds of schools, public schools, private schools, to check that these ratios are invariant. So we can proceed to see if we can put the item the three items on the same scale. So what we have is item that we saw is that ratio, 131 to 140 is this ratio, 131 is common. And if we just multiply that by that, we get that, and we can tell the relative difficulty 127 to 140, or 140 to 127, even though no one has done item 127, no one has done both items 127 and 140. So this is the simple demonstration of what the Rasch model was work started with, because when he was giving reading test to a grade 1 student, and then as the student progressed, you needed to give more and more difficult tests, but the student is changing, so you somehow need to have the relative difficulties independent of the person's abilities. And this is an elementary demonstration of how the items could be connected and put on the same scale, even if not everyone has done all the same items. So in Australia, we have this testing of years 3, 5, 7, 9, and the year 3 are put on the same scale as year 9, and no one has done the same items for year 9 and year 3. Okay. And in fact, if you take the logarithms and do some fancy work on there, you see how the relative difficulties of these 3 items are on a linear scale. I was showing the ratios before, but we take the logarithms. I don't want to get into the statistics here, but this becomes a scale where these 3 items are on the same scale. And ideally, you have many items on the same scale, but this is a demonstration of this. So the question is, what if we had not the evidence that they were invariant with respect to proficiency, and we are concerned about the potential bias for boys and girls? What if they were not invariant for boys and girls? Well, then we could not put the items on the same scale like this. We could not say that we've got a consistent ruler that works the same way for more able and less able people, and for boys and for girls. But we've demonstrated in these data that we can do that. And we use the Rasch model to provide the evidence. So this is the algebra of it, just very quickly. If this is the ability of the person and this is the difficulty, then the ratio of right-wrong versus wrong-right. So this is not just the right response, but the right response in that pairwise sorry, this is just for one item. This is the equation for the right response over that. This is the probability, and this is an example of the Rasch model curve for 3 items, and the proportion of people in these data who got each item right. This is the model from which you get that those analyses that I showed you before comes from this simple model, that the probability of a positive response is simply the ratio of the person's proficiency or ability and the item's difficulty. The denominator here just makes these probabilities go between 0 and 1. But we don't want to spend too much time on that, but this is a very simple equation that you have. So it's a very elementary, simple equation for the case of dichotomous responses, just when you have right, wrong. And okay. So if you want to study for an item that it's invariant, and this was item 131, from the full data analysis and analyze with the RUMM software, you see on the axis here are different class intervals, more or less ability, and grade 3 and grade 5. We can see that this item is the proportion of people getting it right is not dependent on whether 3 and 5. This theoretical curve, the common curve, the observed data are very close to the common relative curve. And so this is the evidence of invariance, no differential item functioning. So this is a criterion that Rasch wrote, and this is a manifestation or a way of checking when you've got a lot of data, and this is an item that's common. It's very important that the relative difficulty of year 3 and 5 for the common items are the same. Otherwise, the scale gets very twisted and you get bias. So we had the variance for boys and girls, different proficiency, but this becomes a very important third requirement of invariance when you're making links and compare across where not everyone has done all the same questions. So there's lots of checks on the invariance. Thank you. Now, it turns out that we can compare, this is a subsample of 1,000 boys, level 3 and 1,000 level 5. This is just straight out data analysis, estimate of person abilities from that set of items, the 65 items. And you can see that the year 3 students are less able than the year 5 students. This is a relative difficulty. All the item difficulties arbitrarily add up to 0. So relative to the average difficulty of the items, we can see the year 3 students are much more able than the year 5 are more able than year 3. But what was very important for the state testing people, so this is content information because you can put them properly on the same scale, is how many year 3 students were almost as good as the best year 5 students. This is really quite impressive, apart from the measurement. And how many year 5 students were relatively poor in their proficiency. So for the educators, these distributions are very interesting, and it's very relevant that you can put the year 3 and the year 5 on the same scale and stretch them both out. If you could only use the common items, it would be a very narrow range of the scale. But with giving unique items, very difficult items to year 5, easy items to year 3 on the same scale, you can draw this picture. Now, you couldn't draw this picture 50, 60 years ago, 70 years ago, before Rasch's work. Now we take it for granted, of course. Okay, thank you. Now, what's interesting from a point of view of connecting to classical test theory and history and so on is that the total score, while we can do all this for the items, there is some concept called a sufficient statistic. And what that means is, in this case, that the total score on the items that a person responded to has all the information about the person's proficiency. There is no more information in the pattern of responses. If there is information in the pattern, that means the model is not working. But if the model is working to characterize the data, or the data are consistent with the model, then the total score has all the information. And that means that you can just use one number for each person. And if you use one number for each person, you can put all the persons on the one line. And it turns out that that insight about statistical models was this Ronald Fisher, the famous statistician of the early last century. And this is the person with whom Rasch studied. And Rasch elaborated the use of this concept, which I showed earlier. The reason you could do those things with the model and eliminate the parameters and so on is because of this sufficiency. Okay. So there's a historical connection between Rasch and Fisher's statistics and concepts. Now, to measure growth, I've just referenced this here, to measure growth, you need to have measurements on the same scale. And the measurements on the same scale are used to illustrate another approach that Rasch had for measuring growth, which had the same principles. But even though I attended lectures of Rasch on growth, nothing has been done before on applying his methods for growth in educational and psychological data. And finally, 50 years later, we do have a book out on the topic. but it requires measurements. It requires that across the different year groups, you've got the same scale. So now we'll get back to some examples of controversy. At the top there, this group, Panayides, Robinson and Times, wrote an article in the British Educational Research Journal that said the assessment revolution that has passed England by, Rasch measurements. So they wrote a very interesting article saying how this work has passed England by, even though it had the opportunity to take advantage of it way back in the 1960s. But Goldstein, another person who was in this field, he argues that the model is inadequate and that claims for its efficacy are exaggerated and technically weak. So these are examples of writing that are for the use of the model and against the use of the model. But very important point to note for us to try to understand this difference is that in Goldstein's argument, it is the model that is inadequate, not the data. There's not that there's a problem with the items, that the items are not invariant. The problem is with the model. And you remember in the early part, I first demonstrated the invariance before claiming the ability to apply the model. If I did not have invariance, then I would not be able to do it. So people need to work very hard at that. But common sense says, not just the Rasch model, that if you want to compare the boys and girls, then the way the items work for the boys and girls should be the same. You don't need the Rasch model to give you this common sense interpretation. If you wanted to compare the heights of boys and girls from different areas and so on, you would want the measuring instrument to work the same. You wouldn't say, oh, we'll stretch the scale a bit for the boys to make them look taller. That the instrument has to work the same way. So it's surprising, but that's part of the controversy, that you can claim it's the model, it's the problem. Where the model is a criteria, from a Rasch perspective, the model is a criterion for invariance. Do you have invariance in the way that I showed? Okay, thank you very much. So let's go to the next slide. So this is another person. Without the Rasch model's claim to item-independent ability measures, Pisa's assertion that student performance, etc., you can read that. So without that claim, you can't do the PISA global rankings. But we would say, well, look, it's not the model's claim. We claim that you need this in the data to make comparisons, but the model can tell you whether you've got this invariance. But the language shifts as if it's, again, a problem with the model. If it doesn't, if there's an incompatibility with the data and the model, it's the model's fault, not the data. Okay, thanks. So in the case of the Rasch model and the model, it is the reason for the model is that it provides a criterion for that invariance. So fit between the data and the model is shorthand, if you've got fit, that you've got invariance. If the response is fit and if persons take some same items, then using a total score is justified, as in classical test theory. But of course, it's more rigorous. You can do all these other features. And this is one of the reasons that typical data that's been constructed with an eye to the classical model about discrimination and targeting, they actually work with the Rasch model, because in classical test theory, you want the total score to work. You don't want the items to have very different discriminations. Items with very bad discrimination are eliminated, and so on. So a lot of data that from tests that have been collected over the years actually do fit the Rasch model, but you can do a lot more with it when you do. So I've been anticipating this point as we've been going through. Now, this idea that a model is a mathematical statement as a criterion, in advanced criterion, a priori criterion, it's not a standard statistical paradigm. You can always argue that the model data fit is not perfect, that the model is too simple. And from a non-Rasch paradigm, when you don't use it as a criterion, what you say is, well, the model is too simple, the model doesn't fit the data, let's look for a model that fits the data better. That's the statistical paradigm, and I'll now give you where that comes from. I've already anticipated it, but I'll make it much stronger. So from one perspective, the model is a simple model for a criterion of invariance. From a statistical perspective, you want the model to fit the data, and if the Rasch model shows some lack of invariance or misfit, so you forget that it's invariance, you just say misfit, then you look for a different model that might account for the data better. Next slide, thanks. So I said that Karl Pearson was a very famous statistician, and he was the most famous statistician before Fisher, and continues to be a famous statistician. And this is not me, this is quoting other people about Fisher, about Pearson's approach to data. Using statistics, the biologists could measure without theorizing. So you don't need theory, you could just measure without theory. You could summarize facts without going beyond them, describe without explaining. So this was seen as a major statistical contribution, that you didn't have to worry about the theory behind the data. Interesting. And so again, this is not me quoting, but because I try to understand the controversy between the Rasch model or the Rasch people and the other people, I was lucky at University of Chicago, I got both. In trying to understand it, it's taken me to this sort of literature. So Pearson analyzed data, biological data, about underlying theory. Pearson had absolutely no time for such a combined approach. He was not interested in the theory behind the data. One aspect of Pearson's approach, the construction of models to fit the data, has, if anything, gained importance since his day. So this perspective of fitting the model to the data is a very strong one, and it comes from Karl Pearson, who was a major contributor to statistics. And of course, for statisticians, that's relatively easy. They search for models, they play around, and they can be quite profound in their work in modeling the data. But what I'm now showing here is that this was the standard paradigm, and when Rasch's work came into the field in the 1960s and 70s, he did his work in the 50s. This is the paradigm against which it was exposed. And when you say item response theory, this is you can see in item response theory the legacy of Pearson. Ron Hambleton, who hasn't contributed anything new in the field, but has written a lot of popular books from the perspective of item response theory. Normally, an assumption is made when fitting an IRT model to a set of data. First, there's the difficulty of finding a model that fits the available data and estimating model parameters. Bock, when the criterion indicates not randomness, an examination of residuals may suggest how the model should be modified to improve fit. Not how the test might be modified, not you might have problems in lack of invariance. The mathematics and statistics has been so abstracted that fit is an end in itself, and it doesn't matter what the model is like, what it does. So you can see the earlier references, the earlier quotes about Pearson, you can see them reflected in the IRT quotes here. Now let's go to the other, we'll now look at the other perspective a bit. The Fisher paradigm. Now these are other people who've written about what Fisher did to statistics. He had a new concept of the role of the statistician, first line. The message was that the statistician should get involved in the practical business of experimentation, not after the fact modeling. The statistician should be involved with the test construction, well, with the experiment, whatever it is. In our case, it's test construction and so on. It was not even enough that scientists should hand their results to the statistician for analysis. Now, one of my problems and our colleagues' problems is that the people come within a lot of data and say, can you analyze this for us? And we do, and we then show them where there's some problems and give them the data back and say, well, we've analyzed it, you've got lack of invariance here, you've got there, and maybe that should have been done earlier. And in fact, in the Australian context, for the test construction for these large-scale assessments, they do pilot studies. They do what is considered a pilot. They give the items to some subgroup. Then they do a trial before they use the items for final assessment. So they are working in experimenting with the items before they use them to measure the state nationwide measurements. So the involvement with the psychometricians, us, the Rasch model people, early on in the test construction is now being implemented. This came from Fisher perspective, experiments, especially large-scale applied experiments that were difficult to control, to be designed by those with statistical expertise. So what in Australia we do, and I'm sure you are doing that now in Indonesia because you've got a lot of Rasch people trained, you will do early Rasch model people, analysts, get involved with early part of the item construction and so on to provide feedback. But that comes from the Fisher paradigm. It's not just a magic from something, and surprisingly, it's in contrast to a statistical standard paradigm. Thank you. Next slide. So if we use what I've just said, apply this to the Rasch model application and Rasch theory, instrument design needs to be a collaborative effort between substantive and measurement expertise. If there's evidence of misfit, anomalies, explain substantively and methodologically. Consider the items, the administration, the preparation of students, and so on. So you study all these content areas and not simply consider that it's a problem with the model. and you take an empirical and content action rather than finding a different model. So to kind of summarize, incompatible paradigms, the debate can be polemical, that is, people argue, and it's almost like politicians are arguing. There's no, it's not a pleasant argument, but that's standard. Historically, if you have a new paradigm, you create controversy. So Pearson, within the world of statistics, Pearson's legacy has been the strong one. Modeling data without theory, and if the model does not fit the data, you find a more complicated model. The Fisher legacy, on which Rasch measurement theory rests, is theory-driven instrument design and statistical analysis. So that's the difference in summary, and it has this history that goes way back to the fundamental key people historically in contribution to statistics. So this is not just a Rasch model debate; it's a deeper debate. Now, Rasch was aware when he first wrote his work, and in his 1960 book, and I've taken this quote, he started to some degree, because he was a mathematician who turns to statistics, and he was a very capable statistician. He published statistical papers. Even he shifted in his own paradigm, because he asked this question. It is tempting, and this is a quote from him, including, I think, well, this italics. It is tempting, therefore, in the case with deviations of one sort or another, to ask whether it is the model or the test that has gone wrong. So he was aware that one perspective was the model is wrong. But there's another perspective that maybe the test has gone wrong. And in one sense, this, of course, turns the question upside down. So he was aware in the 60s or late 50s that what he was doing was turning the question upside down. That is, upside down from the standard perspective at the time, except for the Fisher perspective. But in another sense, the question is meaningful. So Rasch himself was not talking about paradigms or anything like that, but he knew that this turns the question upside down. Is it the model or the data that's wrong? And that's the core of the paradigm difference and the source of the controversy. Next slide. Thank you. So thank you very much for listening. I hope that wasn't too quick. Yanti has this set of slides now, and you have the slides obviously because you brought them up, and the other papers that I referenced. I'm happy to take some questions if you have questions.
Yes, thank you very much. Okay, thank you, Professor Andrich. A very insightful lecture here. So we already take some question, and then I think the admin, can you show one of the question, please? All right. So this come from Mr. Januar Pribadi. The question is, in your opinion, what are the most prominent criticism and challenges faced by the Rasch theory, and what strategies or modification can be employed to address and enhance upon in theoretical and practical aspect. So
Yes,
it's a bit
and this is
philosophical.
this is a very good question, and it becomes relevant a lot. It becomes relevant not only in your practical work and so on, but when you try to publish papers or get research grants or volunteer to use this, because of the typical criticism will be that the model is too simple or something like that. And then what's very important is to articulate or to say, but what we want is invariance of comparisons to a sufficient degree. It doesn't have to be perfect. No model fits perfectly. Even if you're complicated and you have a 3-parameter model, you have to admit that the data don't fit the model perfectly. They just fit it better because there are more parameters. But if that parameter is not invariant, and so on. So you have to take the argument back to the requirement of invariance, and that it is possible to get it invariant enough, and that this criterion is powerful. So and that it's simple. Now, an interesting example that Ida and I and Yanti knows, because it was in Yanti's thesis, I'm sure, that one of the areas for educational testing where there's the argument about the model fit and so on is if you have multiple choice items, and then there's potential for guessing. The Rasch model doesn't have a parameter for guessing. Yanti knows, and we have some papers on how you deal and set up a scale that's invariant, taking account of guessing. But that, the way we do it, characterizes exactly the difference in paradigm. We take some data out, and you're nodding there, obviously you know it. We take potentially guessed data out to get the item difficulties. We do not try to model guessing, which to us by definition is random. It's guessing. How can you model if so that is an example of where we try to deal with a legitimate criticism. You don't get the item difficulties properly from the Rasch model if you have a lot of guessing in the data, and you can't really deal with that with multiple choice items, but you do to some degree. For example, the Australian assessment now has, because it's online, they do what's called adaptive testing. If a student has got some questions right, they get more difficult questions. And when you do that, you get less guessing in the data because the students are not doing items that are too difficult for them. So it's a very good question. You go back to invariance and you go back to understanding how you can deal with the data to solve the problem rather than finding a model, and hopefully you can give an answer. So the guessing one is a very good example of how we handled that question about the work. Incidentally, what we do with the guessing, which and RUMM has it all, you can do it almost automatically in our program in RUMM. That work we built on a fellow student who was dealing with this problem at the University of Chicago when I was a student, 71 to 73. But somehow this has not been mainstreamed even in other Rasch programs. So it's very interesting, and it's a nice example. And thanks for your question. There are challenges, and I try to get back always to the variance issue. And then if there's legitimate criticism, as in guessing, how we can deal with it.
All right. Thank you, Prof. Andrich. I think this is the same case like missing data too, right? So because of the predictable of person location and item difficulties, so the possibility they can correct answer from missing data also is possible to be identified. All right.
Yeah,
so can we move to the second question? Yang kedua, Mas? Okay. So this is a very favorite thing. So what is the real difference between Rasch model and IRT PL1? So I always have this kind of question when I deliver the workshop. Okay, so simple question, I always answer that in IRT they have some kind of constant. Rasch don't have a constant, but we want to know what your answer about this. Please.
Well, from an algebraic perspective, there is no difference. But so it's a paradigm difference. For them, there's a sequence. So if you've got multiple choice items, there's a sequence. There's what they see is the 1-parameter model, the 2-parameter model, and the 3-parameter model. And if the 1-parameter looks like there's some misfit, you go to the 2-parameter. And if you've got guessing, you go to the 3-parameter. From the Rasch model perspective, it is the model of invariant comparisons for dichotomous data, and there is no second or third model. This is the only model for dichotomous data that has invariant comparisons, that has invariant parameters. So there's no algebraic difference, but the way you use it has this major difference. And it's the difference between IRT and the Rasch theory. How you use it. Do you just treat it as one model, but you can have any other model? Or if that beta model don't work, do you think about the data? So it's a philosophical difference, not an algebraic difference. Well, it's more than philosophical. It's actually what you do as a consequence of any misfit. In one case, you go back to the data and the items and the test and try to improve that. In the other one, you find a more complicated model. So it is a paradigm difference.
I see. All right. Okay. So can we move? Thank you, Mr. Adil. So can we move to the last one, please? All right. So Professor Andrich, this is also there's a lot of question that you are on the side of hardliner unidimensional Rasch model. So another person always questioning, is there any alternative when we see to unidimensional? So the question is something like this, okay? Given the fact that unidimensionality is one of the measurement requirement of the context of Rasch model, what is your position of the multidimensional Rasch measurement model developed to handle data with multidimensional factor structure? So many people are always questioning about this. Is it Rasch truly only deal with unidimensional data variable, and what about the other alternative? Okay, please, Dr. Prof. Andrich.
Yeah, you can in some cases structure. In fact, in the polytomous data, Rasch first started that you could have multiple parameters for a person. If you've got 3 categories, you could have 2 person parameters and 2 basically threshold parameters. That you can have a structure that sets up invariant comparisons, but they're of a multidimensional structure, so that the parameters of the items are independent of the parameters of the people. But my feeling is that when you have the typical measurement, they are multidimensional aspects that look like the Rasch model, but then the question is, what do you do? It is possible to have an additive structure for two variables that works together. So, for example, you could have a maths test in which you try to model both the reading component and the mathematical component. On the other hand, you could argue, but reading mathematics questions is an integral part of mathematics, but you have to vary the questions and so on. So I would then say, so how are you going to use your multidimensional Rasch model? How are you going to make comparisons? What's the point? So I would first want to construct tests that are unidimensional. They may then be correlated, but I've got this test that's a mathematics test, this test that it's a reading test, and of course they tend to be correlated because students who are good at mathematics tend to be good at reading and the other way around. But yeah, my disposition is that it's a better understanding if you work on constructing tests that are relevant to the curriculum, the syllabus, and so on, that are unidimensional. Both of them separately, that you get a tight unidimensional variable, and then you can study the degree to which those variables are related in your population, rather than try to disentangle the dimensions after you've constructed your test and say, oh, well, this is multidimensional. Because in some sense, everything's multidimensional. Yeah.
Okay, thank you. And then there are some questions already posted here also. I think I tried to just select some of them. So for example, the first one from S2 Widodo, Universitas Muhammadiyah Malang. He asked about the sample size in the RAS context. Okay, so what is the answer for that one? So I think he want to say that there is some certain way in terms of using what we call deciding sample size in the RAS that analysis. Can you answer for that one?
Yeah. Obviously, the bigger the sample size, the greater the precision. But you have to be aware that the greater precision can be so great that nothing fits. So that's true in all statistics. If you've got a t-test for some real data between two groups and you've got a sample size of 10,000, you're definitely going to get a significant difference, even if it's very trivial. So this is a statistical issue. The sample size depends in the context and the situation. When you're doing linking, those common items, you need enough of a sample size to provide you evidence of misfit. Our guidance, but it's not like a prescription, is that for every parameter you estimate, you need at least 15 or 20 people. So if you have 40, and that's how many people should be responding to that question. So if you've got an ordered category item with 4 categories, that's 3 parameters, and you've got 10 items, that's 30 parameters. We would think you need at least 400, 450 people. But other things are very important. That is that the distribution, there's no point having 10,000 people all with the same score. So you need some range of performances to capture the relative difficulties. So other factors need to be looked into for the sample size, and not just, oh, this is a sample of 700 and that's good, because if the 700 are all very skewed and all in the same spot, 300 well distributed would be better than 700. So the sample size needs to be taken into context.
Sure.
Again,
thank you very much.
You want information across the continuum and so on. So that's where you need people. So you need to deliberately try to select less able people, more able people, and so on for your instrument design.
Yes, thank you. I think this add also another information, I think, from my clinicals who are doing calculation about sample size based on the precise of measurement. Right. So, Prof. Andrich, I think another question from Zahran would like to ask you, can you explain a bit mathematical model in multifaceted RAS measurement, many facet RAS model? Okay.
Yeah.
From Muhammad Zahran, right? So
yeah. I don't know if Yanti ever used it in RUMM, but it's actually got a facility in RUMM. It's not a separate program. You can just use it. The facet structure arises. Incidentally, just a bit of history. My long before we had these programs and models and so on, my thesis at the University of Chicago was a two-facet structure. And that's and then Mike Lineker came and he picked it up and he did a lot of good work at it. The structure arose from, we had graders assessing writing. So we had multiple graders assessing writing of multiple people. So we had 50, 60 essays graded by 7 or 8 graders. And what became clear when we looked at it closely was that the graders were different. That is, even with some training, they wanted to be different in their difficulty. Okay. So now, if you've got multiple pieces of writing and multiple graders grading students, you have a two-way design on the items effectively, because the difficulty of the item depends on the difficulty of the essay and the harshness of the grader. Mm-hmm. And what we tried to separate was the harshness of the grader independent of the difficulty of the essay, and the difficulty essay independent of the difficulty of the grader. So the two-facet structure, that's an example of a two-facet structure, is when there is a structure on the items. You can design a structure on the items that's not just different graders if you design your items in particular ways. So it's a structure on the items rather than the structure on the people. The structure on the people is when you have boys and girls and city and country folk and different countries. That's a design on the people. When you have what I just described, like graders and items and so on, that's a design on the item. So the facet structure is a design on the questions, in which you've got more than one element contributing to the difficulty. But you can try to envisage that it is simply additive. Difficulty of the question, and then it's more or less difficulty depending on the harshness of the grader, and you can add those up.
Okay. Thank you very much, Dr. Andrich. I think also need to inform that unidimensional RAS model is not a single model. So we have a dichotomous model, and then the one that you invent, RAS rating scale. Another one is a partial credit, and the last one is many facet RAS model. Right. So I think the time is come to the end. So thank you very much, Dr. Andrich, for the wonderful sharing and then enlighten us. So for this, we would like to say very thank you to have you here. Okay, and then for that, back to the MC, Miss Mbak Anissa. Thank you.
Thank you, Dr. Bambang, for leading the session, and also Professor Andrich for the comprehensive presentation.
Thank you very much.
A quick reminder for all.
I was just going to say,
a quick reminder for all participants. The committee has shared the attendance list at the chat box. Please do not forget to fill it. Now, before we end this session, we will invite Dr. Yanti to deliver the closing remarks. Dr. Yanti, please.
David, you want to say something, please?
I was just going to say that the questions were very good questions. So it seems like people were, I wasn't talking to a blank board. The questions were very relevant. Thank you very much.
Thank you. Thank you.
Yes. Thank you very much, David. Yeah, the people who are who joined this session actually are very interested in RAS model, and they have been working perhaps for some times. But your lecture is as always is insightful, and I'm sure this will stimulate for further study for us and me as well. So 1 hour is very short and it's not enough. I think we hope that we can arrange some other time for next lecture, maybe for polytomous perhaps. Thank you very much. Yes, thank you very much, David, for your time and then for your lecture. Yes.
Thank you.
Thank you, David. Thank you.
Yeah. Bye-bye.
Yeah. Yeah, keep
Thank-
healthy. Thank you.
Nice to see
Uh,
everyone again.
Nice
Yeah.
to see you. Yeah, thank you. Thank you, Bu Yanti.
Yeah.
Terima kasih,
Anissa,
Pak
Pak
Baru.
Bambang.
Terima kasih.
You,
Thank you,
thank you.
everyone. Yes.
Oke, Mbak Anissa bisa tuh close.
Distinguished guests, ladies and gentlemen, we have now reached the end of this event. Thank you for your active participation, and we look forward to having you again on another occasion. Wassalamualaikum warahmatullahi wabarakatuh.
Okay. Thank you, Bu Yanti. Terima kasih, Pak Bambang.
Terima
Nisa.
kasih.